Raj Chandra Bose was a student of pure mathematics during his university years and began his career as a college teacher of mathematics. Chance then resulted in his being drawn into the development of statistics in India. From that point on, he was, for many years, an important contributor to the subject. After his move to the United States, he became closely identified with the foundation of mathematical theories of experimental designs and information codes. The strong interplay of these ideas, based on physical properties of designs and abstract properties of finite mathematics, resulted in a unification of various types of designs and codes that suggested the existence of a few more fundamental principles in finite mathematics. This program is devoted to the later years of Professor Bose's career, when he returned to studies of pure mathematics and brought with him concepts of designs and codes that could be used in the modern development of theories of graphs and partial geometries.
On the business of finite mathematical structures, or so-called combinatorics, you had been using them like this more and more ingeniously in applications to statistics and coding theory. And by 1963, you had become deeply engrossed in the study of such structures for their inherent, intrinsic mathematical interest. Did this represent a completely new departure for you?
No, it didn't represent a completely new departure. What happened was that I now became interested in the study of the structure of designs, especially designs and association schemes, especially using graph theoretic methods. But I didn't care about whether this would be of any practical interest to statisticians. Otherwise, I kept to my old things, so it was not a completely new departure. But those mathematical properties, at least up to this time, have not been of any interest. This can't be said that they won't be of any interest or any use in the future.
That's true. That was said years ago about finite geometries.
Yes.
Intrinsic but no applied interest. And you showed a lot of that was wrong. Well, you have seen the significant interconnections between designs and graphs, the graphs of graph theory.
Yes.
How do you perceive this?
Well, let us look at it in this way. Firstly, I will have to explain to you what an association scheme is. First, let us see M-class association scheme, and then I will come to two-class association scheme. An M-class association scheme is a thing like this. There are V objects or treatments. Conceive them, say, as balls.
In the air, balls and...
Balls,
okay.
yes.
Yeah.
These V objects. Now, firstly, any two of these objects have either to be first associates, second associates, third associates, or mth associates.
Okay.
Let us conceive of m different kinds of colors. If two balls are ith associates, I join them by a string of the ith color.
I see. Okay.
So this is one property that we ought to have, that The second property that we ought to have is that every object has exactly n sub I ith associates. That is, if you take one of the balls,
Yeah.
then exactly I strings, n sub I strings of the ith color will proceed from it.
Okay.
Thirdly, we ought to have this property, that if two of these objects are ith associates, then the number of the jth associates of the first one and the kth associates of the second one has got to depend only on I, j, and k, and nothing else.
I see. The colors, in other words.
Yes. And we call this number p sub j k super I. So that if you look at this structure that we have formed, the number of triangles whose bases are of the ith color,
Mm-hmm.
and one of whose sides is of the jth color and the other of whose sides is of the kth color. This number is fixed, whichever base of the ith color I choose.
Mm-hmm. Mm-hmm.
So such a thing is an M-class association scheme,
All right.
if these V objects have these properties. Now let us consider a two-class association scheme. In a two-class association scheme, things become simpler. There are only two colors. Instead of two colors, we can do like this. If they are first associates, we join them by an edge,
Okay.
call the balls our vertices. If they are first associates, we join them by an edge. If they are second associates, we don't join them by an edge. Then this is exactly a graph,
I see.
because a graph is a thing of this kind,
Mm-hmm.
which has V vertices, and any two vertices are either joined or are unjoined.
I see.
So a two-class association scheme is exactly equal to this kind of graph. I call these graphs strongly regular graphs,
I see.
because they are regular. Through each vertex proceed the same number of edges in virtue of the property number 2.
Yes.
But it has more because of the third triangular property.
Mm-hmm.
So I call these graphs strongly regular graphs. And these were found to have a great connection with the design of experiments. For example, there is the question of characterizing association schemes. The first association scheme was the triangular association scheme, which arose in connection with the story I have told you about Uden
Yes.
at that conference. Just take a m by m square
Mm-hmm.
and let the diagonal be empty,
Okay.
and on the upper side of the diagonal fill it by the numbers 1, 2 through m times m minus 2
Okay.
in any way you like.
Yeah.
And on the lower side of the diagonal, just symmetrically. Now call two objects first associates if they occur in the same row or in the same column. If they will occur in the same row, they will also occur in the same column.
Mm-hmm. Mm-hmm.
And if we calculate, we are able to show that this is now a two-class association scheme. If two objects occur in the same row, we will call them first associates.
Yes.
If they do not occur in the same row, we will call them second associates.
Mm.
And this is exactly the scheme on which the Uden's design was based. The rows of this scheme can be taken as the blocks of the design.
I see.
Now we can ask a question like that. All right, let us calculate the parameters of this, namely the numbers n sub 1, n sub 2, which we have just defined,
Yeah.
and these pi, jk things. of which only 2 are really necessary. If we calculate P sub 1, 1 super 1, and P sub 2, 2 super 1, then the other Pijk's are all constant automatically by mathematical theory. Now we ask this question. Suppose there is an association scheme, somehow or other we have got it, 2-class association scheme, which has the same parameters. Now, will it always come from this kind of thing which I have described?
I see. An interesting question.
Yeah, that's the question. Interesting question. Connor first introduced this question. He was one of my PhDs, a very bright student. And he showed that if m is greater than 9, the answer is yes. Later on, Srikhande and Hoffman and other people showed that if m is 7, the answer is m is 7 or less, the answer is yes. But in the case of 8, it was found that there were 3 other association schemes which had the same parameters.
I see.
But would not come, could not be arranged like this.
Yes.
Similarly, we can take a square and make it into a Latin square, that is, each symbol occurs once in each row and once in each column, and call 2 of the fill in by n square numbers, and call 2 of these numbers first associates if they occur in the same row or in the same column, and call them second associates otherwise. Then it will turn out that this is again an association scheme whose parameters we can calculate. And again we can ask the same type of question. Srikhande showed that if n is greater than 4, then the answer will always be yes. But there is one counter example for the case n equal to 4. From this also follows another interesting thing. Bruck was associated in this, was interested in this kind of thing. Suppose you take a complete set of orthogonal Latin squares and knock out 1 out of it. It's a folk theorem that we can replace it. Again, let us take r minus 2 orthogonal Latin squares of a certain side k. If we were able to construct a complete set of orthogonal Latin squares, we would have k minus 1 orthogonal Latin squares. Therefore, k minus 1 diminished by r minus 2. So many are missing now. And this is called the deficiency. Now, if we had a deficiency of 2, Bruck was trying very hard that we can do it. In came Srikhande's letter, because we were at a certain meeting in Santa Monica, Bruck and myself, Harari and other combinatorial people, and came Srikhande's letter. There is one counter example here. If you take a cyclic square of order 4, then there ought to be 3 orthogonal Latin squares to complete it. 4 minus 1 is 3. But we cannot do it, we know it. But Srikhande deduced from his theorem that since there is only that one exceptional case, in every other case, if 2 orthogonal Latin squares would be missing, that we would have something of deficiency 2, we can always complete it. I had just given a lecture on association schemes, and Bruck was at my back. He said, what is the use of these association schemes, and so on. But after this, he was very enthusiastic, and he produced a nice formula that if we have something of deficiency D, and then if the sides K is greater than a 4th degree function of this deficiency, fourth degree polynomial of this deficiency d, then we can always put this back.
Good gracious.
And he used very interesting methods. I told Brack that, look, this work of yours and Connor's and Srikande's, I think it might be possible to put them all under one umbrella, deduce them from a single theorem. That is how my interest in it arose. And from this I conceived, after a great deal of thinking, I am very proud of that paper, the concept of what I call partial geometries. The partial geometry is a thing like this. There are V points, and 2 points may be either joined by a line or not joined by a line. Each line has k points. Through each point there pass r lines. And there is a further property that if a point does not lie on a line, then we can draw exactly t lines to cut this line, baseline, and therefore t minus r minus t lines will be left dangling. They won't intersect this baseline. And I showed that from this all the previous work can be deduced because that T association scheme which we used in Uden, that can be regarded as an association scheme, something like instead of the parameters RKT here, we will have 2M2. And similarly for the Latin square association scheme and other association scheme, I produced a formula generalizing Brack's methods. If he would have generalized his own work, it would have been his thing, but he just didn't believe me. So I produced a formula that if k is larger than a certain function of r and t, then you can construct an association scheme from a partial geometry, of course. If 2 points are joined by a line, we can call them first associates. If they are not joined, we can call them second associates, and we can construct a strongly regular graph. So the question is whether if we have an association scheme with these parameters which come from a partial geometry like this, whether we will be able to put it back in a partial geometry, whether I called it that if a scheme is pseudo-geometric, is it really geometric? That is, can we really find a partial geometry from which it comes? And I showed that if k is greater than that function of r and t, then the answer is yes. And from this, all the work of these previous authors just falls out.
Beautiful.
That is how I came to it. We did something on 3-class association schemes with the help of Dowling and Renu-Laskar and other things. This is one of the things.
Well, it looks as if there were a lot of interconnections between designs.
Yes, there
of your kind of definition and graphs.
Graphs. We found many other theorems, but this is not the place to describe all the theorems. I had a nice combinatorial school going in Chapel Hill at that time, the members of which were myself, Dowling, Renu-Laskar, K. Smith, and I. M. Chakravarti. And we regularly met in a seminar, read other people's papers, and did things on our own.
With all this new work progressing, along came age 70 in 1971, at which moment you retired as Keenan Professor of Statistics at the University of North Carolina at Chapel Hill, and followed Horace Greeley's advice to the young, go west to Colorado State University in Fort Collins, the pleasant host for this interview. As Professor of Mathematics and Statistics here, you have seemed super active ever since arriving, right up to the time of your retirement last September and beyond. What lines of investigation have been occupying you?
In the first instance, my major interest has continued, namely the interconnection between the design of experiments and graph theory. But I have also produced 6 PhDs in mathematics and 1 in statistics. I have written an article for combinatorics and combinatorial theory with another joint author for the Encyclopedia Britannica.
Yes.
I have continued my travels, and I have been active in various other ways, as the editor of, or rather on the editorial committee of various journals of mathematics and statistics. I was president of the Institute of Statistics in 1971, 1972.
Yes.
And all these things.
And something like 25 papers.
Yeah, and wrote about 26 papers.
Ah,
That
good number.
rate of production has continued on the average number ever since my coming to the United States in 1949. In India, the rate was about 2.5. Here, the rate has been about 3.
Very good.
And I have now 145 papers altogether. As for research, I will just give you 2 examples. One is the work on the embedding of quasi-residual designs, which was done in cooperation with my student Srikhande and his student Singhi. Singhi was in Bombay. That part was done by writing to each other,
Yes.
whereas Srikhande was visiting professor here. First, I must explain what a quasi-residual design is.
That would be good.
Consider a balanced incomplete block design with V treatments and V blocks, K replications,
Yes.
and block size K,
Yeah.
and every pair of treatments coming together lambda times. Now it is well known that if we have any such symmetric balanced incomplete block design, then any 2 blocks always intersect in lambda treatments. If we cut out 1 block and all the treatments in this block, then lambda treatments will be cut out from each of the remaining blocks, and therefore all the remaining blocks will be of size k minus lambda. And it can be proved that what we have left, though it is not a symmetric design, is still a balanced incomplete block design. Now, this design is known as the residual of the original balanced incomplete block design.
Yes.
Now, there is another design which we might have got by hook and crook in any different way,
Yes.
which has the same parameters as the parameters of a residual design. Then that design is known as a quasi-residual design.
Good.
The question is whether it is really the residual of some balanced incomplete block design or not. For the case lambda equal to 1, this is trivial, because the original design in that case will always be a projective plane, and its residual design will be an affine plane. An affine plane can always be extended to a projective plane, and a projective plane, by cutting out 1 line,
Yes.
we can always make an affine plane.
Yes.
For the case lambda equal to 2 is not so trivial. It is a very difficult proof, which Connor, my student, and the well-known mathematician Marshall Hall,
Yes.
jointly together succeeded in solving for the case lambda equal to 2.
Mm-hmm.
They proved that the answer is yes. This was done in 1953. One of my students, Bhattacharya, he produced an example of a quasi-residual design of a very peculiar type. Consider the balanced incomplete block design with V equal to B equal to 25, R equal to K equal to 9, lambda equal to 3. Then its residual design has the parameters V equal to 24. No, I'm sorry. The V equal to 16,
Yes.
B equal to 24,
Yeah.
and R equal to 9,
Yes.
K equal to 6, and lambda equal to 3.
Aha.
Now, any design which these parameters is a quasi-residual design. It may be the residual of a design, or it may be a quasi-residual design.
Yeah.
He produced an example in which two of the blocks are intersecting in 4 treatments. It cannot be the residual of a balanced incomplete block design, because if it had, then the utmost they could intersect is in 3 treatments.
Yep. Yep.
This is known as the Bhattacharya case.
I see.
So in general, therefore, the answer is no. There are counter examples to the situation where there will be a quasi-residual design which will not be embeddable in a resolvable design. Lawless proved that for the case lambda equal to 3, if K, the block size, is greater than 28, then the Bhattacharya phenomenon cannot occur. Srikande and Singhi proved that for the case lambda equal to 3, if K is sufficiently larger, then it's always embeddable.
Okay.
Now the proof of Srikande and Singhi is very difficult,
Yeah.
and they make so many different cases.
Yeah.
Now Srikande was visiting professor here at that particular year, and as I was coming out of my office on the steps, suddenly it flashed on my mind
I see.
that we should not use graphs, but we should rather use multigraphs.
Oh.
That is, if the treatments are taken as points,
Yeah.
then if they come together lambda times, we should join them by lambda arcs
Aha.
rather than by just one.
Very good.
And from this flowed a generalization of partial geometries, which I have already explained to you. These I called partially geometric designs rather than partial geometries. Instead of the parameter R, K, and T, we have now the parameters R, K, T, and C.
Okay.
I showed that if C equal to 0, then it will reduce to an old partial geometry,
Okay.
RKT. Then using these, the connection between multigraphs and designs, it turned out that a quasi-residual design always produces a certain multigraph. And using these multigraphs and generalizing my previous methods,
Yeah.
we were able to show that firstly, if K is larger than a certain cubic function of lambda, then the Bhattacharya phenomenon cannot occur.
Fine.
If I put in that cubic function lambda equal to 3, lawless's number 28 just drops out. Secondly, we were able to prove that if k is greater than a certain fifth degree function of lambda now, which is a sort of rather complicated function, then it is always embeddable. But if k is less than that, it may or may not be. The question is still open.
Very good. Yeah.
That is what I proved.
Very good.
I will now give you a second example.
Good.
The second example was partially balanced arrays were defined by I.M. Chakravarti long ago. Srivastav called them balanced arrays. And he and his students made many interesting optimal designs using these balanced arrays. Hariharan Iyer, a statistics student, was working with me for his statistics doctorate.
Yeah.
And we generalized the idea of balanced arrays to what we called G-balanced arrays.
Yeah.
Here we use a certain group G and balance the arrays with we show that we can have arrays which are invariant and balanced with respect to this group G.
I see.
And using these, I asked him to devise methods for factorial designs of the type 2 to the power m times 3 to the power n. These designs are very frequent and useful. In his thesis, he actually produced designs of resolution 3. And he also gave the method for designs of resolution 5, though they required a little more computation.
Yes.
And the computation of these has not yet been done. Some of our students are now doing it because he has been employed on the faculty of the CSU.
Very
Two
good.
papers came out of it. One will be published in the Festschrift, which we are giving to Dr. C.R. Rao, one of my first students and the most brilliant student,
Fine.
who is an FRS, Fellow of the Royal Society.
Yes. Very
He is
good.
now 60 years old, and the Festschrift is written in his honor.
Good.
So one paper has been given to this Festschrift and has already been accepted for publication.
Very good. Well, you've been busy. Very, very well busy, it would seem to me.